Boyer has stated that Euler did for the calculus of Newton and Leibniz what Euclid had done for the geometry of Eudoxus and Thyatides. One of his groundbreaking works was a book including infinite analysis in 2 volumes, in which he summarized numerous discoveries in infinite series, infinite products, and continued fraction. We will explore Euler's proof that every rational number can be written as a finite fraction. Euler would go on to show that irrational numbers can also be written only as infinite continued fractions. Euler defined continued fractions to be fractions in which the denominator is the sum of an integer and a fraction, and the denominator could continue to be defined in like manner for any number of iterations, even to infinity. He describes 2 forms of continued fractions. In the first, all the numerators are 1, and in the second form, they could be any whole number. We will show how to write any rational number as a finite continued fraction. The method that Euler describes relies on what we now call the Euclidean algorithm. So Euler proved that the quotients will give the integers in the successive denominators of the continued fraction. Since every pair of numbers has a common divisor, we see that there is not only a finite continued fraction equivalent to any rational number, but we also have described a way that we can find that fraction. Let's walk through an example. First, divide by 59, then we'll divide 59 by 45, 45 by 14, 14 by 3, and 3 by 2. Divide 2 by 1 to complete the process. Here I've highlighted the quotient, and then we can see that 1461 over 59 is equal to this continued fraction. Hold on, I see a problem here. That works for improper fractions when the numerator is bigger than the denominator, but what about expressing a rational number as a continued fraction when the denominator is larger than the numerator? You can do this by simply finding the reciprocal of any continued fraction previously expressed. It's simple. Keep everything the same, just add another layer with a 0 plus term at the beginning. What about irrational numbers? When taken one line at a time, the continued fraction would converge on the exact rational number in a similar way that a convergent series converges to a value. This led him to consider infinite continued fractions. You could observe the continued fraction converge toward an irrational number even when the continued fraction did not end. Here we have an example, and we see that this can give us the infinite continued fraction for the square root of 2. This raised a question for myself. If the continued fraction for the square root of 2 is given with 2's as the integral part of the denominator, is this true for every square root? Euler anticipated that question as well. He did provide an infinite list of square roots. Could be written as infinite continued fractions. From what I saw, none of them look quite as neat and tidy as the square root of 2. Changing the integral part of the denominators to 3, you are in effect increasing the denominators and therefore obviously decreasing the value of the continued fraction. However, the square root of 3 is larger than the square root of 2. He did, however, express both e and the square root of e as infinite continued fractions. Euler's prolific skill in mathematics seems to be unmatched, and through his writing, he was able to convey complicated concepts in ways that could be understood by others not at his level.